Hello, welcome back to my channel. In this video, we will learn about model evaluation. This video will guide you through the essential aspect of model evaluation in machine learning, covering key metrics, techniques, and consideration for building robust and reliable model. From understanding accuracy, precision, recall, and FN score to evaluate curves, you will gain a comprehensive understanding of performance metrics. Special attention will be given to handling challenges like overfitting, underfitting, and class imbalance. Additionally, we will discuss advanced evaluation techniques such as cross-validation, confusion metrics, and error analysis to provide a deeper insight into model performance. By the end, you will be equipped to critically access model and implement strategies for continuous improvement. Accuracy matrices, precision, recall, and FN score. Precision measures how many of the predicted positive cases are actually correct. High precision means fewer false positive, but it does not account for missed true positive. It is crucial in scenario where minimizing false positive is essential, such as in spamming filter, where incorrect labeling, legends, emails, or spam must be avoided. Recall. Recall measures the proportion of the actual positive cases that we correctly identify by the model. High recall means fewer false negative, ensuring that the most positive cases are detected. It is crucial in scenario where minimizing false negative is crucial, such as indices diagnosis, where falling to identity a condition could have a serious consequence. FN score. The FN score balance precision and recall, provide a harmonic mean. It is useful when both false positive, negative are undesirable. Confusion matrix. Confusion matrix is a powerful visualization that helps you to understand the different types of error. It shows the actual class level against the predictable class levels, allowing you to calculate metrics like precision, recall, and accuracy. Validation. K-fold cross-validation. This technique involves dividing data into K-fold. The model is trained on K-1 fold and tested on remaining folds. This process is repeated K times, with each fold serving as a test once. This average performance across the all-key fold for the most robust evaluation. Benefit of cross-validation. Cross-validation helps mitigate the risk of overfitting by evaluating the model performance on unseen data. It provides a robust assessment of the model's generalization ability and ensures reliability performance metrics. Additionally, it allows for better tuning and selection. Regression matrices, R-square and mean-square error. R-square measures the proportion of the variance independent variable explained by the dependent variable, indicating the strength of the relationship between them. It evaluates how well the regression model fits the data, with value ranging from 0 to 1. A higher R-square value indicates a better fit, meanwhile the model explains a greater portion of the variance. However, it is important to note that a high R-square doesn't always imply model accuracy, as it does not account for overfitting or the relevance of the predictor. Mean square error MSE. It calculates the average square difference between the predicted and the actual value, providing a measure of model's overall error. By squaring the error, it emphasizes large deviation, making it particularly sensitive to outliers. A low MSE indicates a better performance model, as it reflects small prediction error and closer fit to actual data. However, MSE is scale dependent, meaning its value increases with magnitude of the data. Despite these limitations, MSE is widely used in integration tasks to evaluate and compare the model performance efficiency. Handling imbalanced data addressing class. Undersampling. This technique involves randomly removing samples from a majority class to balance the dataset. It can be effective for reducing computational cost, but may result in using valuable information oversampling. This technique involves increasing the number of samples in the minority class. It can be done by duplicating existing samples or generating synthetic samples. It helps to reduce bias but can lead to overfitting if does not done carefully. Cost sensitive learning. This approach assigns different costs for misclassification based on the relative importance of each classes. This helps to address the bias introduced by unbalanced data and prioritize the correct classification of crucial classes. Cost sensitive learning accounts for unequal errors. In financial application, misclassifying a fraudulent transaction as legitimate can be far more costly than the misclassifying a legitimate transaction as fraudulent. This highlights the need of assign different costs to different types of error, ensuring that the model prioritizes minimizing the more cost mistakes. In medical diagnosis, failing to identify a serious illness is far more determined than incorrect diagnosis someone with illness that does not have. Cost-sensitive learning helps prioritize minimizing false negative, ensuring greater accuracy, and reducing the risk of overlooking critical conditions. Receiver operating characteristics ROC and AUC area under curve. The ROC curve plots the true positive rate against the false positive rate for the different classification threshold. This curve threshold visually illustrates the trade-off between sensitivity and specificity. The AUC area under curve provide a single metric to quantify the model performance. A higher AUC value indicates better performance, meaning the model is better at distinguishing between positive and negative cases. Interpredictability and the Feature importance. This helps to understand the relative influence of each input feature in the model prediction. By identifying the feature that contribute the most to the model decision, it provides valuable insights to the model behavior and decision-making processes. Feature importance analysis can guide for feature selection, improve model interpretability, and enhance performance by focusing on the most impactful variable. Model interpretability. Interpretable models are easier to understand, allowing us to reason about their decision and gain confidence in their predictions. Interpretability is particularly crucial in high-stakes applications such as healthcare, finance, and legal system, where transparency and trust are essential for ethical and reliable decision making. By understanding how a model arrives, it predicts stakeholder can ensure fairness, detect bias, and validate result. Then we comes to the conclusion. First, evaluate the multiple matrices. Use a combination of relevant metrics to get comprehensive understanding of your model performance. Second, performance cross-validation. Ensure robust model evaluating by utilizing cross-validation techniques. Address class imbalance. Use appropriate techniques to handle imbalanced dataset and avoid bias. Fourth, consider cost-sensitive learning. Account for unequal error cost when appropriate, prioritizing accuracy in crucial area. Interpreter mode result. Analyze feature importance and model behavior for transparency and trust. That's all for the video. Please do like and comment. Thank you.